Welcome to Module 10, where we are covering chapters 11 and 12 from the textbook, and we'll be mainly focused on proof methods for quantifiers. We've got four main learning objectives for this module. The first two come from chapter 11, and the second two come from chapter 12. We'll be interested in translating English sentences containing multiple quantifiers to first-order logic. And there are a few pitfalls that you should be aware of. But ideally, you've taken a few mathematics courses that have used quantifiers and are familiar with sort of nested quantifiers or multiple quantifiers. We'll be interested in sort of rewriting some of these more complicated sentences into a nicer format where we move all of the quantifiers out to the front of the sentence. And when we're in that format, we'll refer to it as premix form. And it's a lot like CNF or DNF for propositional logic, but now in the case of first-order logic where we allow for quantifiers. So we'll say a bit about that and give a good example. And then from chapter 12, we'll start talking about some informal proof methods for quantified statements. And these are used all over the place in mathematics. So we'll also give a couple of good examples of some classical proofs, the infinitude of primes, and also the Barber paradox in our last couple of slides. And then finally, we'll finish off talking about sort of the axiomatic method for the blocks world, and we'll introduce the shape axioms and finish off that sort of story. And in particular, these are the axioms that are used in the proof checker for ANCON in Fitch. So we'll say a bit about that axiomatic method, and that'll be it for this particular module. Okay, so let's say a bit about what happens when we have multiple quantifiers and some of the pitfalls that students will often fall into when trying to understand the meaning of these particular sentences. So the first is here in this blue bubble. When you're evaluating a sentence with multiple quantifiers, don't fall into the trap of thinking that distinct variables range over distinct objects. So for example, if you have an x and a y in your sentence that are both variables, it could very well be the case that x and y are exactly the same. So it doesn't mean that they're distinct from each other or that they're different. And in particular, that first bullet point holds true. If you have that sentence that says for all x and for all y, the sentence p of xy is true, well, that will logically imply that for all x, p of xx is true. And again, that's because when we're quantifying over those x and y, it could be the case that x is equal to y. And then in a similar sort of vein, we have the second bullet point there that says that if you have a sentence like there exists an x that satisfies p of xx, well, that will logically imply the sentence there exists an x and there exists a y such that p of xy. And again, the reason why is that we don't make any sort of distinction between x and y. They could be the same thing. And in this case, if there's one that satisfies the sentence by plugging into the first component and the second sort of component, well, then you can be sure that there's an x and a y, in this case they're the same, that make p of xy true. So again, be careful when we have distinct variables. It does not mean that they are referring to distinct objects within the domain of discourse. In the previous slide, we talked about multiple quantifiers, but only when the quantifiers were the same. So we had two existential quantifiers or two universal quantifiers. There are some pitfalls that you should be aware of as well when you're using sort of two different quantifiers at once. And really the most important thing here, and the textbook does a great job of giving some good examples of this and some details. So I recommend that if this is sort of new information to you, that you read those examples sort of carefully and hopefully convince yourself of this important fact that when you're dealing with mixed quantifiers, the order of those quantifiers is incredibly important. So if you say something like, for all x, there exists a y, such that r of xy, well, that is not the same thing as saying there exists a y, such that for all x, r of xy. I think the textbook gives an example where r is the sort of predicate, x likes y, and the domain of discourse is people. And again, it's clear that the meaning of those two sentences is just completely different. But it's tempting to sort of lump them in as the same by just sort of swapping the quantifier order there. But again, be careful when you're writing these sentences down. The order of the quantifiers matter. And this is also particularly important when you're translating an English sentence that may have multiple quantifiers in it back into first order logic, because you have to know what the intended meaning of those quantifiers was. And that's not always possible, or there might be multiple interpretations for a given English sentence. But to sort of translate it correctly, you have to sort of know the meaning that they had intended for it. And the reason I bring that up is that sometimes that can be inferred from the context of whatever the sentence is being sort of stated in. But nonetheless, you need to be incredibly careful about the order of your quantifiers, because again, it can change the meaning of the sentence and whether or not the sentence is even true or false. Okay, so let's take a bit of a detour and talk about section 11.6. It's not quite related to our learning objectives, but the authors make an excellent observation here about function symbols. They make the observation to sort of justify why they've sort of omitted them from the textbook so far, or haven't really been emphasizing them. But in our class, we've tried to emphasize them quite a bit because they're really useful for mathematics, as we've pointed out in the past. And again, this observation they make points out a bit of detail about why it's also useful for mathematics. Okay, so what do they say, or what's in the textbook? It says the following: anything that you can express with an n-ary function symbol. So that means sort of n inputs when you're building up these complex terms, can be re-expressed using an n plus 1 ary predicate symbol. So here I say relation symbol, but the textbook uses relation symbol, but they mean a predicate symbol here. So we could introduce a whole new predicate symbol. We'd have to pay the price, though, by increasing its arity by 1. And if we do that, then if we also have the identity predicate, which we always do in a first order language, then we can express anything we could have expressed with that function symbol. And again, because the arity is increased, we pay the cost here of increasing the complexity of the sentence. So again, they're sort of mentioning this, and they give some good examples. I don't think we need to go over the examples because it's not related to the learning objectives. But nonetheless, they sort of talk about this process of how this works. And I think they're sort of justifying their lack of function symbols. But notice that sort of in reverse here, function symbols can be useful in the sense that, if we were just dealing with predicate symbols, we might be able to get away with less predicate symbols by introducing a function symbol, and the arity would be decreased for every one of these function symbols that we would introduce. And what results are often far more compact statements than what you might get if you weren't using function symbols. Okay, so this process is interesting. And it also just shows that they're a bit redundant, right? We could have got away without introducing function symbols at all. So the most important part of chapter 11 is the discussion of the prenix normal form, and we'll need it in subsequent modules. So it'll be important for us to really understand what this prenix normal form is, and in particular, how to get a sentence into a prenix normal form. You should sort of contrast it and compare it to the CNF and DNF form. That's the disjunctive normal form and conjunctive normal form, back from propositional logic, and sort of think about it as a form of that, but in the case of quantifiers. We say that a sentence is in this premix form if any of the quantifiers that are contained in it are all the way out in the front of the sentence. So they don't appear anywhere on the inside or in between some sort of truth functional connectives. All of the quantifiers are appearing right at the front of the sentence. I mean, there can be as many as you'd like or even none at all. But all of the quantifiers that do appear in the sentence appear right out in the front. And it turns out, and we'll see sort of how to go through that process here in a moment with a good example, any sentence at all is logically equivalent to one in premix form. Okay, and it may not be tautologically equivalent, but it's just logically equivalent. And then down here on the bottom, I've just given an example of something in premix normal form. It's got two universal quantifiers and an existential quantifier, but you'll notice that they're all out in the front here. And the scope of all of those quantifiers is that full well-formed formula there on the right. And this would be the sort of format for premix normal form. So here we've got an excellent example from the textbook that we'll go through step by step, because as we go through the steps, you'll see all of the sort of general methods you'll need to sort of take a sentence and put it into this premix normal form. So here we'll be analyzing the sentence that's given in English at the very top. So every cube to the left of a tetrahedron is in back of a dodecahedron. And if we translate that sentence into first order logic, we obtain this sentence here that's been sort of highlighted in orange. So we have that universal quantifier over the variable x, and then we say that x is a cube, and there exists a y, which is a tetrahedron, and x is to the left of y. And if that statement is true, then there is going to exist a y, which is a dodecahedron, and x will be in the back of y. So we could have done that by this sort of step-by-step translation process. But you'll notice that when we do that, that natural translation results in a sentence that has quantifiers that are not out in the front. So here, what we would like to do is start walking through this process that you see down below, and we'll go step by step and explain the details of what's happening one by one. Okay, in order to save on space, the textbook first abbreviates some of the predicates. So cube gets sort of abbreviated with a C, tet gets abbreviated with a T, left of with an L, dodec with a D, and then back of with a B. And so that first line that you're seeing is just a rewriting of that sentence that we translated in orange. Now, the first thing that we have to be aware of when we're putting things into premix normal form is that quantifiers often are difficult to work with when we're sort of confronted with a conditional. So the textbook sort of recommends that the first thing you do is you take those conditionals that are appearing and convert them over to truth functional connectives that don't include the conditional. So remember, P implies Q is the same thing as not P or Q. And so here on that first line, we are just replacing that conditional with something which is tautologically equivalent to that sentence inside of those brackets. And again, the reason why is that our quantifiers, when we want to start pulling them out to the front, will work much more easily or better with our conjunctions, disjunctions, and negations. So this will be the first step if you see a conditional in your statement. Now, as you work through pulling these quantifiers out to the front, you'll also want to work from sort of the inner part of the statement, so the very first sort of connectives that you're sort of seeing, and then move outward as you go through the process here. But again, that first step here is to deal with that conditional. So moving from line 2 to line 3, we now start identifying those quantifiers that are sort of the most interior in the sentence. And the first is that existential quantifier highlighted in blue. Now we use the null quantification principle to then pull that quantifier across that conjunction and right out into the front next to that negation symbol that we had from the previous step. Now we can pull it past that c of x because the c of x doesn't have the variable y appearing inside of it as a free variable, and therefore we can use that null quantification principle to pull that out to the front. So here we've started to pull that quantifier out to the front. Now moving from line 3 to line 4, we applied De Morgan's law for our quantifiers, and we pull that existential quantifier through that negation, or we maybe think about passing the negation through the quantifier, that green one. And when we do that by De Morgan's law, that existential quantifier in blue becomes a universal quantifier. And that negation then negates the sentence that the quantifier was applying to. So that's where we get this line in 4. And that's really what you'll do anytime that you're confronted with the negation of one of these quantifiers. You just apply De Morgan's law and push the negation through, and that allows the quantifier to start moving out to the outside of the sentence. So now let's focus on the piece highlighted in red. Here, what we're doing is changing the variable for the quantifier from a y to a z. And remember, when we're working with quantified statements, the variable used doesn't really matter at all. So those two sentences are logically equivalent to one another. But there's a good reason for doing this. So in our previous step, we were working with that green universal quantifier, and you'll notice that that variable was y. And our new quantifier that we're focused on, the one in red, that's the next quantifier in our sentence, is using the same variable. However, the two quantifiers themselves, the scope of those quantifiers is not overlapping, right? So the one there in green is on that sentence that has C, T, and L, and the one in red has that sentence that has the predicates starting with D and B. And because they don't overlap, it's perfectly fine to use the same variable in this particular case. Now, when we start pulling that existential quantifier in red out to the front, we're going to need to pass it past those two predicates, T and L, that have a Y in them. And in order to do it in a way that keeps the sentence logically equivalent, we need to first change that variable to something else. So just recognizing that the y already appeared in the other universal quantifier, that then tells us now in this step that we need to convert to a different variable. And again, here we've converted to z. And the sentence is again equivalent because the variable doesn't have any meaning. It's just a placeholder for a position inside of the predicate. Now that we've changed that variable from a y to a z, we can pull that universal quantifier that has the variable y next to it, which I've highlighted in pink here, all the way out to the outside of the sentence. And now you'll notice that it applies even to that sort of disjunct, starting with that red universal quantifier attached to the z. Okay, and again, that's made possible now because we've changed the scope of that quantifier from having the variable y to having the variable z. So let's finish it off by now pulling that existential quantifier out to the front. I've highlighted it here in gray. And we're sort of going through two lines at once. The first thing that we do is use the null quantification principle to add an existential quantifier out in the front there of that sentence that's negated. So that's the one that has the C, T, and L. And we can do that because those predicates don't have the variable z in them at all. So putting the existential quantifier out in the front is logically equivalent to not having it there. And then on the next line down, we pull that existential quantifier out to the front because it sort of works nicely with the disjunction. And then that second to last sentence is in pre-nix normal form. So we have those three quantifiers out in the front, the two universal quantifiers, and then the existential quantifier. And so we're technically in pre-nix normal form. But the textbook goes one last step and converts the negation and disjunction back into a conditional. And that's because the original sentence had a conditional in it, so it sort of puts it back into the conditional. But, if you were on a quiz or an exam or something like this, and it was asking you to put it in pre-nix normal form, then that second to bottom sentence would be more than enough. And again, we'll sort of need this sort of format later on. And really the key here is that if we follow these steps that are outlined here, and these are really the only steps that we would need, we can always take any sentence and pull those quantifiers out to the front. So now that we've talked about the pre-nix normal form and given an example, we're ready to move on to chapter 12 and start talking about some of the informal proof methods for universal and existential introduction and elimination. And these are the methods that we'll formalize in the next chapter into our Fitch-style system. We'll move sort of quickly through these because they're pretty commonplace in mathematics. I mean, they're sort of general methods that are used pretty much day to day in mathematics classrooms. Okay, so the first one is universal elimination, and this is also sometimes called instantiation. If you've established a universally quantified statement for all x, s of x, and we know that we have a name, C, for some object in our domain of discourse, well then we're free in our proof to infer that C has the property that sort of is represented by that predicate S. In other words, S of C is actually true. Okay, again, so the idea here is just that if it's true for everything, then it's true for anything that we have a name for. So we're free to sort of substitute that in. Another similar and sort of equally trivial rule is existential introduction, and this sometimes goes by the name of generalization. And what it says is the following. If we've established that the predicate S is satisfied by some object named by C, in other words, S of C is true, and we know that C is in our domain of discourse, so what we're referring to, then we can infer the quantified statement, there exists an X, S of X. So this is how we would introduce an existential quantifier into maybe a formal proof. But the idea is that if we can show that it's true for something in the domain of discourse, then we're free to establish the existentially quantified statement. All right, so universal elimination and existential introduction are fairly straightforward and almost trivial. On the other hand, existential elimination and universal introduction will be a bit more involved. So again, existential elimination is sometimes called instantiation. And it says that the following is true. If we've already established that the existentially quantified statement, there exists an X, S of X, is true, then we're free to give a name, let's call it, say, C, to some object in our domain of discourse that satisfies this predicate S of X, as long as that name is not already in use somewhere in the language. And when we do that, when we introduce this sort of new name, then we're free to assume that S of C is true and then use it within our proof. So in other words, if we know that the statement is true, then we can introduce a name for some object that actually satisfies that particular predicate. And you'll notice that we go from a statement that doesn't have an existential quantifier to one I'm sorry, that one that does have an existential quantifier to one that doesn't have an existential quantifier. And this will, when we're formalizing these methods, have sort of a new feature in our Fitch program for introducing these sort of names. But for now, if we know that existentially quantified statement is true, well, then we can name something that actually satisfies the predicate. Okay, so we have one more rule to talk about, or informal proof method. That's the method of general conditional proof. We'll also refer to that as universal introduction or generalization. And this is common practice in mathematics courses. And in fact, there's sort of a certain phrase that appears whenever you're using the method of general conditional proof. In a general conditional proof, you're trying to prove a statement of the form for all x, p of x implies q of x. In other words, all p's are q. And the way that you go about it is to choose a name that's not in use at the moment. And let's say it's C. So again, it's not part of your language. You just introduce this new constant symbol. And again, here we're going to call it C. And you assume the statement P of C is true. So you just take some arbitrary C and you assume that it satisfies the predicate. And then you argue or you prove that that same constant has to satisfy that predicate Q. In other words, every P is a Q. And if you're able to do this, then you're entitled to infer the desired universal quantified statement. And in fact, in mathematics lectures and textbooks, it happens so often that you hear the statement or you hear something like, let R be an arbitrary real number or an arbitrary natural number or an arbitrary function. And then they'll proceed to sort of walk through and prove something. And when you say that it's an arbitrary real number or an arbitrary function, you're saying that it sort of satisfies some statement P of X. But again, hopefully that's a familiar sort of process. On the next slide, I'll sort of remind you of two famous proofs from mathematics that use these methods. Okay, so let's talk a bit about two famous proofs from mathematics that utilize these informal proof techniques. The first is that there are infinitely many prime numbers, and the proof that we'll look at is the one that's due to Euclid. Here we'll sort of translate his result into a mixed quantified statement in the following way. For all x, there exists a y such that y is bigger than or equal to x, and y is a prime. In other words, there's always a larger prime. So to prove this mixed quantified statement, we begin by assuming that x is an arbitrary natural number. We then consider all of the primes that are less than or equal to x. You multiply those prime numbers together and then add 1. Now, this new number that you obtain won't be divisible by any of the primes less than x, less than or equal to x. And that's because when we divide by one of those primes, we'll get a remainder of 1 because of the fact that we added 1. Now, because it's not divisible by any of those primes, any of its prime factors have to be bigger than x. And therefore, we have a prime number which is bigger than x. Notice that this uses the method of universal introduction and existential introduction. First by considering an arbitrary x, and then by identifying a y in the domain of discourse. Another interesting proof that uses these informal methods is the Barber paradox of Russell. Now, the Barber paradox of Russell asks us to consider a town which contains a barber with the following property. For every man that lives in that town, the barber shaves that man if and only if he doesn't shave himself. Russell then asks us to consider the barber who is a man that lives in that town. And what we find is that the property leads us to conclude that the barber shaves himself if and only if he does not shave himself. which is clearly a contradiction. Okay, so what you're seeing here in green is just a first order formalization of that statement. Here it says there exists a z and there exists an x, such that z is a name for a town and x is a name for a barber. And furthermore, x is a man of town z. And furthermore, for every other man in that town, the barber shaves that man if and only if they do not shave themselves. So that sentence there highlighted in green is exactly the statement of the barber paradox. And as I said before, if you consider the barber themselves, then you arrive at a contradiction. And by negation introduction, the negation of that sentence there in green is a first order truth. And in fact, it really didn't even depend on the meaning of the predicate man of or shave. We could have replaced those with any two separate two-ary predicates and arrived at the same first order truth. Now that we have our informal proof methods for quantifiers and we can make mixed quantified statements, we can completely introduce the axioms we need for the shapes in Tarski's world. And these are exactly the axioms that are used in the ANCON program when it's searching for a formal proof. So these are the main assumptions that would be made in those proofs. We've already previously talked about the basic shape axioms, 1 through 4, because those only required a single quantifier. But now we have axioms that allow us to introduce the predicate same shape and eliminate the predicate same shape. And this requires 6 more rules, and that's because we need rules for each of the various shapes. So for 5, 6, and 7, they have basically the same format. If you have any two objects and they're both cubes, then you can conclude that they have the same shape. The same thing is true for any pair of dodecahedrons and any pair of tetrahedrons. And then in terms of elimination, if we know that two shapes are the same, so xy satisfies the predicate same shape, and x is a cube, well, then we can eliminate the same shape and obtain the cube y predicate. In other words, cube has to have exactly the same shape. And likewise, the same thing can be done for dodec and tet. And these last 6 axioms are all that are needed to prove all of the statements in Tarski's world that are true about the shapes.